Okay, today we're finishing up on stereochemistry. I need to tell you a short story about drug development and chiral molecules and how they interact with biology. And then we'll move on to chapter 6 and talk about how and why organic reactions happen. So one of the reasons we care about whether two things are enantiomers or diastereomers is that enantiomers have to have the same chemical and physical properties, except how they interact with polarized light, and except with how they interact with other chiral molecules. I'm not going to say anything today about how enantiomers interact with polarized light. That's a subject that's covered in your chapter. You should know how to calculate enantiomeric excess based on optical rotation. It's not that difficult, and so we're not going to spend any class time on it, but you should be familiar with that. Not because I'm going to ask a complicated question on it, because I'm really not. Any question I could ask on that would be pretty easy, but because it may be something that you encounter in a future standardized exam. I don't know whether MCAT or DAT asks about enantiomeric excess, but if it does, I want you to at least have some basis for it. I will say, though, that diastereomers do not have the same chemical or physical properties, and that goes not only for molecules that are diastereomers of each other, but even temporary non-covalent complexes that are diastereomers of each other. So shown here, I have an overlay of images from two X-ray crystal structures of a bacterial enzyme in complex with one of two, well, the overlay is the complex between the enzyme and one enantiomer with the complex of the enzyme and another enantiomer. So the same protein bound to one enantiomer in orange and then the other enantiomer in purple. And of course, the protein is made of chiral amino acids. So the protein itself is chiral. And you'll notice in the overlay, so this is a ribbon diagram of a protein structure. You maybe haven't seen something like this before. There's a lot going on there, so let me just orient you a little bit. It's called a ribbon diagram because we're not showing all the atoms in the protein. Instead, we're showing a cartoon that gives you a sense for where the backbone of the protein is, and then we're showing you side chains. In this image, in the protein, all of the carbons are gray, all of the nitrogens are blue, all of the oxygens are red. The little red dots, the little red spheres, are all water molecules that co-crystallized in this image. Water, of course, proteins exist in water. Water is floating around, so you can sort of ignore them. I probably should have eliminated them from the image. Okay, so here is a side chain that has a nitrogen, a carbon, another nitrogen, and then another nitrogen. Here is a similar looking side chain. There's one that has an oxygen in it. Sorry, I thought that was there's the laser pointer. This is the one with the three nitrogens that I was talking about. Here's one of those imidazole type side chains, a 5-membered ring with 2 nitrogens in it. And then this spiral here or that spiral there, that's the ribbon diagram cartoon of the protein backbone. So we're seeing a lot of the side chains, we're not seeing the backbone, and then here we're seeing where 2 different inhibitors bind in the active site of the protein. The orange inhibitor has an S stereocenter. The purple inhibitor has an R stereocenter. They are enantiomers of each other. And you can see they bind in this protein completely differently. The 6-membered ring portion is overlaid pretty well, but because the stereocenter here has opposite configuration, in the purple enantiomer, the rest of the molecule juts out to the right, where it's near this side chain. In the orange enantiomer, the rest of the molecule juts out to the left, where it's near a bunch of other side chains. So the point is, what I'm showing you is an overlay of two diastereomers. The diastereomer where the protein is bound to the R enantiomer, and then the diastereomer where the protein is bound to the S enantiomer. And you can see they fit in there differently, all right? And conceptually, this is exactly the same as we talked about last time with the handshakes, right? Your hand is chiral. You shake somebody, you're with your right hand, you shake somebody else's right hand. That is one diastereomer of a handshake. You shake somebody's left hand with your right hand, and that is an entirely different enantiomer, right? Or an entirely different diastereomer. The right on right handshake is a pleased to meet you. The right on left handshake is sort of an enchanté kind of weird experience handshake, right? It's diastereomer situations, right? Okay, so that you must understand to appreciate what's coming next. Chiral molecules bind to proteins differently, okay, because the non-covalent complexes are diastereomers of each other. Questions about that? Okay, so that means that drug molecules that have stereocenters in them, you have a potential challenge where two enantiomers of the same drug might have distinct and different biological effects. Now, there's a horror story in US drug development history of an antiemetic, that means an anti-nausea drug, anti-throwing up drug, that was prescribed to pregnant women to help with morning sickness. It was called thalidomide, and one of the enantiomers turned out to be a teratogen, meaning it causes mutations and developmental problems in the growing fetus. So women were taking this drug and at the exact wrong time to be exposed to a teratogen. And that was one of the earlier demonstrations that you've got to be really careful about the effects of not only the desired enantiomer, but also the undesired enantiomer. Since then, the FDA doesn't approve drugs where, so got to back up a little bit. It is easier synthetically to make a one-to-one mixture of enantiomers than it is to make the pure enantiomer. And that will become, the reason why that's true will become clear as we get into reactions. But for now, if you remember that it's easier and cheaper to make a one-to-one mixture of enantiomers than it is to make the pure enantiomer, you'll understand what we're talking about. Another term that I'm going to use is a one-to-one mixture of enantiomers is called a racemate. And I don't know where that term came from, but we'll just write it down here. Racemate is a one-to-one mixture of enantiomers. So it's always easier to make a racemate than to make a pure enantiomer. And because of that, people that do drug development know this, and so they will often generate a drug as a one-to-one mixture of enantiomers and demonstrate that the other enantiomer, if they can, they'll demonstrate that the other enantiomer, the one that's not as biologically active, doesn't have any negative effects, okay? So if it's a case like thalidomide where the other enantiomer is a teratogen, obviously you don't sell or market the racemate. Instead, you just purify and make the one enantiomer and you make that, right? But if the other enantiomer doesn't have any sort of majorly negative side effects, the drug company will just sell the mixture of enantiomers. Do you guys understand what I'm saying, where in biology you expect one enantiomer to have the desired biological effect and the other one to be different? So you're going to have an active one and then an inactive one, or a less active one. And as long as the less active one doesn't do anything problematic, it's cheaper just to sell the mixture of the two, all right? So this is a drug called citalopram, marketed as Celexa. It's one of the first selective serotonin reuptake inhibitors prescribed for depression. There are many others now, but this is one of the early ones. It was invented in 1972 by a company in Denmark and approved for use there in 1989. The clinical trials and drug development took about 15 years. It was finally approved by the FDA in 1998. So you were not alive then, but I had already graduated. I was on my mission in 1998, so wow. In any case, the FDA approved it, but United States patent protection for drugs is that you have 14 years, I think maybe it's 17, from the time you file a patent for a drug to have exclusive rights to generate and license your molecule. And at the end of that, the patent expires, and then other companies can make and market that molecule. That's called when a drug goes generic. You guys know about that, right? That you can get generic drugs cheaper. Why? Because there's more competition, more people making it, you can get it cheaper. So in 2003, citalopram, which was marketed as the racemate, the one-to-one mixture of enantiomers, went off patent, which meant that other companies could make it. And that often causes a massive drop in revenue to the company who originally made it because they can't charge as much of a price. That's called a patent cliff. And if you work for a drug company in business, you're constantly worried about this because you've got a cash cow that's generating money, but you know in a few years it's going to go generic and then you've got to have something else. So the patent expired in 2003. Well, what are you going to do? One of the tricks that drug companies use is shortly after the racemate gets approved, they develop an enantioselective synthesis. That is, they make only the active enantiomer. Now, I told you that's harder, but here's why they're doing it. You can get a new drug approval from the FDA for just the active enantiomer. This allows you to extend the patent lifetime of your drug. What you do is you argue that, hey, we previously sold you the racemate, now we've got this new pure enantiomer, and they will argue that the effects of the pure enantiomer are better because you're not taking 50% of a molecule that doesn't do what you want, and maybe there were some side effects. And so they will argue that it's better for you to take the pure enantiomer, and it will certainly be better for them if you do. And the reason for that is that just about the time the patent on the racemate expired, they filed a new drug application in 2001 with FDA approval in 2002. So that was a way for their business to mitigate the risk. As soon as the patent cliff for the racemate was there, they had gotten approval to market and sell just the pure enantiomer, which they called appropriately S-citalopram for the S enantiomer. So if you see ES at the beginning of a drug name, you know it's the pure enantiomer and that it's S. If it were R, I don't know if they would say AR, like R, like a pirate, but anyway. So in 2009, after the patent was approved for S-citalopram, you could get 28 tablets, this is data from the UK, 20 milligram tablets for 1.25 pounds, okay? Now look at the price on 28 tablets of 10 milligrams of just the pure enantiomer. More than 10 times as expensive. By the way, why are they giving you 10 milligrams of the pure enantiomer versus 20 milligrams of the racemate? It's the same amount of active drug, right? It's just that the racemate has 10 milligrams of dead weight in there, okay? And what I'm saying is not always universally true. Sometimes the undesired enantiomer has a similar biological effect, it's just less than. Or sometimes it doesn't do anything but has some side effects. So it's a case-by-case basis, but basically this strategy is called patent evergreening. It's a way to basically double the lifetime of your patent protection by getting all the mileage you can out of the cheaper racemate and then switching to the pure enantiomer and trying to convince physicians and patients that the pure enantiomer is better for them. In the case of citalopram, there was some indication that it was modestly superior. S-citalopram was modestly superior in efficacy and tolerability relative to the racemate. But it was not at all clear that that modest superiority was worth a 10 times increase in price. So some of you aspire to be physicians today, and someday aspire to give prescriptions to people. There will be drug sales reps coming to your office to try to convince you that you need to prescribe certain things to your patients. If some guy comes to your office and says, hey, I have the pure enantiomer now, you should really switch your patients to that. That might be true because the pure enantiomer might be superior, but you should also take into account cost and whether the benefits are worth the cost. So there are multiple stories like this. If you want to go read about them, you may have heard of omeprazole, which is an anti-heartburn kind of drug. It lowers the amount of stomach acid that you make. Same sort of thing. It was marketed as a racemate and then sold after that as a pure enantiomer. That was the difference between Prilosec and Nexium. There used to be commercials on TV for that when I was a kid. There are other examples as well. For example, ketamine that you may have heard of. S-ketamine is a painkiller and an anesthetic. The R-enantiomer is a potential hallucinogen. So you sort of have to be careful there. There are, anyway, others. Ibuprofen, though, is sold as a racemate, and it's not a problem. The S enantiomer is 160 times more effective than the R enantiomer. But, and this actually happens a lot of times, biologically, if you take the mixture, your body can convert the R enantiomer into the S enantiomer, and so that works out just fine for ibuprofen. It doesn't work out great for thalidomide, even if you gave somebody just the pure enantiomer that was the antiemetic. Biologically, your body removes a proton from the stereocenter just by acid-base chemistry, creates an intermediate that's not chiral and that gets protonated back, and you make both enantiomers anyway. So it's not safe to take thalidomide as a pregnant woman in any amount, because even if you only take the R enantiomer, your body's going to process the drug and make it both of them, and then you're going to get the teratogenic effects. So these are things that drug development companies worry about. If you've ever opened up the package inside of a medication and seen the big layout of all of the data, this kind of thing is in there. Stuff to think about and stuff to worry about. Any questions? Anything you want to know about that? Yeah.
So when a new medication comes out and they always talk about the long list of side effects, could that be due usually to the racemate?
So the question is the long list of side effects of various medications. My favorite is do not take whatever it is, Skyrizi, if you were allergic to Skyrizi. Like, you think? How do I know if I'm allergic to it? I don't know. Listen, when I turn on Hulu advertises autoimmune disorders to me. At some point, it's going to start advertising various aging products to me. But anyway, yes, we get a lot of drug commercials when we watch Hulu. But in any case, sometimes the list of side effects could be associated with the other enantiomer. Some drugs are actually not chiral. There's no other enantiomer. Side effects can happen for a lot of reasons. One of the major reasons is just that biology is complicated. You make a drug that's supposed to bind one thing, and it will do that, but there might be other things you didn't intend that it's also binding. And so that's kind of the problem. Yeah?
Do you have any way of predicting whether, like, for instance, ibuprofen, we know the body converts the enantiomer to the active enantiomer? So,
sure.
like with other drugs, in the future, when you're building it, you may not figure out what's going to be more effective and what's going to be
Yeah, so can you predict whether, and conversion of one enantiomer into the other is called racemization, because you're taking one pure thing and eventually making a racemate. You can predict that sometimes. There are characteristic structural patterns. So if you have protons at stereocenters that have lower pKa's, that can be a great indication. For example, with thalidomide, this proton here is alpha to a carbonyl, and the conjugate base is resonance stabilized. So that's a key structural feature that we'll talk about in 352, where if you saw that, you would predict, okay, maybe we're going to worry about racemization there. For ibuprofen, it's probably the same thing. The proton that would be removed is adjacent to a carbonyl and a benzene ring, so the conjugate base would be stabilized by resonance. And so it's possible that, yeah, your body can remove this proton. We'll talk later, but if you look at the conjugate base of thalidomide, that's no longer a stereocenter. You've lost stereochemistry. When it reprotonates on that carbon, it can do so from either above or below. You get a mixture of enantiomers. Okay, other questions? All right, so that thus ends stereochemistry. It's going to continue to be an issue. We're going to continue to talk about it, but that's your crash course in stereochemistry. What we want to do now is spend some time talking about how and why reactions happen. Okay, so reactions, the reason why reactions happen is called thermodynamics. And this relates to, that's a C there at the end of thermodynamics. This relates to the equation that you learned in general chemistry. Processes that happen are processes where delta G is negative. And there are two components to free energy. There's this component, which is enthalpy, and then there's this component, which is entropy. Now, we've talked about entropy before. It's related to disorder, and reactions that increase disorder have a favorable effect on delta G. For enthalpy, the consideration is basically, are the bonds that you make in a reaction stronger or weaker than the bonds that you broke during a reaction? That's essentially the question. If yes, the reaction's going to have a favorable enthalpy. And if the answer is no, the reaction's going to have a positive enthalpy, which is going to be unfavorable. For the most part, in organic chemistry, when trying to get a sense for whether a reaction is going to be favorable or not, we're going to focus on enthalpy and the strength of the bonds that we make versus the bonds broken. We will also take into account qualitatively disorder. Most of the time, the change in entropy for a reaction is going to be small. There are times when the change of entropy in a reaction isn't small. So I'm just going to put a little asterisk here and say that you want to beware of reactions that make rings or cyclize. That requires a loss of entropy. You want to be aware of reactions where two things become one. That requires a loss of entropy. You also want to be aware of reactions where one thing becomes two. Reactions that make rings are going to decrease entropy. Reactions where two things become one are going to decrease entropy. Reactions where one thing becomes two are going to increase entropy. And then reactions where one product is a gas are often going to be very entropically favorable, because the gas is going to bubble out of solution and go out into the air, and entropy will increase dramatically. So those are factors that you sort of want to be aware of, not to take into account mathematically, but just have a qualitative sense of when entropy is going to tilt the balance between starting materials and products. Let's talk about enthalpy. You could, of course, measure the enthalpy for a reaction. There's a whole field in chemistry that our department here was very, has a historical strength in. Years ago, it's called calorimetry, where you essentially measure the heat that's given off as a reaction happens. But now we tend to use data that already exists about enthalpy for various other reactions and use it to calculate what we expect for a given reaction. So there are tables of values in your text that are called bond dissociation enthalpies, and we're going to talk about these briefly. So what is a bond dissociation enthalpy? It is essentially how much energy you have to put in to break a bond. Back when we, sometimes people call bond dissociation enthalpies BDE. Sometimes they call it delta H with the, that's fine. Imagine for hydrogen, do you remember when we talked about, so many weeks ago, when we talked about bonding in hydrogen, how you could bring two 1s orbitals together to get a sigma bonding orbital and a sigma star anti-bonding orbital. This energy distance here between the break-even point of the atomic orbitals and the sigma bonding orbital, that is the bond dissociation enthalpy. That is how strong the bond is. That is how much energy you have to put in to promote electrons back to their starting state. So, for example, for hydrogen, the bond dissociation enthalpy for this reaction, where you break the bond between the two hydrogens, and each hydrogen takes an electron and then moves on, that bond dissociation enthalpy equals plus 105 kilocalories per mole. If you prefer kilojoules, it's about 4 kilojoules per kilocalorie per mole. That means you have to put in 105 kilocalories per mole of hydrogen in order to split hydrogen into its two hydrogen atoms. These bond dissociation enthalpies are all for what we call homolytic bond cleaving. That means you break the bond and it's not like one partner gets both electrons and the other gets none. They each get one. That's sort of the reference point. These little half-hooked arrows that we're using, that's the symbol for one electron moving. If the arrow had two little flags at the end of it, that would be 2 electrons. If it has one, that's just 1, okay? Notice that bond dissociation enthalpies are always positive because breaking bonds requires energy. This maybe allows us to push back on something you may have learned, which was true but only from a certain point of view. Thank you, Obi-Wan Kenobi. How many of you have ever heard that breaking bonds releases energy? Somebody told you probably in biology that, yeah, ATP is unstable, and when you break the bond in ATP, it releases energy. That just like, as a chemist, there are things that sort of bother you, and that's one of them. Breaking bonds always requires energy. What they're talking about with ATP, breaking bonds, releasing energy, is not the bond breaking part. It's the formation of the new bonds afterwards, okay? So you have to sort of tease out all of these details to get really accurate chemical intuition. Breaking bonds is always uphill in energy. That should make sense to you now because bonding allowed 2 electrons to move down in energy in the first place. Reactions are favorable when the bonds you make are more stable than the bonds that you broke. Let's give you an example of this in terms of some simple chemistry, and then maybe I'll show you an example of ATP so that we can correct what you've learned over the years. Okay, so here is a reaction that we're going to talk about and that we'll learn about in detail next week. It's a substitution reaction. We're going to replace the chloro on the carbon with an OH group, and we'll replace the OH in water with Cl. So this is a substitution reaction. So if we wanted to predict whether this reaction would be favorable or not, we're going to make the assumption, because we've got the same number of things over here as over here, we're going to make the assumption that delta S is pretty close to 0, and if that's true, we can judge how favorable the reaction is based on the change in enthalpy for a reaction. Okay? So what we're going to do is total up the bond dissociation enthalpies for the bonds we break, and compare that to the bond dissociation enthalpies for the bonds that we make. All right, so what bonds do we break in this process? What bonds over here are not present over here? Yep, you got the carbon-chlorine bond, so let's write that down. We're going to break the carbon-chlorine sigma bond. What else? Yep, the hydrogen-oxygen sigma bond we're also going to break. Now we're going to make which bonds? You make hydrogen-chlorine, you make carbon-oxygen. All right. So now there is a table in your text, and it's, I think, both in some of it's in chapter 7, some of it's in an appendix at the end of the book. We're going to look up bond dissociation enthalpies for carbon-chlorine bonds. And this is going to be how much energy you have to put in to break the carbon-chlorine bond. All right, so that's, if we look that up, that would be 331 kilojoules per mole. I prefer kcals, but these numbers are from the table, and I didn't bother to convert them into kcals because I was lazy. But again, it's about a 1-to-4 relationship between a kcal and a kilojoule. Okay, breaking of the hydrogen-oxygen bond is 498 kilojoules per mole. And again, those are positive numbers because breaking bonds is always uphill in energy. Now, how about the bonds that we make? We make a carbon-oxygen bond. The bond dissociation enthalpy for a carbon-oxygen bond is 401 kilojoules per mole. Now, if I'm making the bond, should this number be positive or negative? Negative, right? So you're going to look in the table for bond dissociation enthalpy, and the number's going to be positive, but when you're using it to predict a reaction, you turn it into a negative number if it's a bond you're making. Does that confuse anybody, or are we okay with that? When you make a bond, flip the bond dissociation enthalpy to be negative, okay? So there we go, and for HCl, that bond is 431 kilojoules per mole. All right. So now we can basically add all of this up, the bonds that you break versus the bonds that you make. You add all that up, and you would come to the conclusion that that's downhill by overall -3 kilojoules per mole. Okay? Or alternatively, something like, okay, we'll actually do the math, shall we? Divided by 4.184, or about 0.7 kilocalories per mole. So it's not hugely downhill. The change in enthalpy for this reaction, and therefore the change in delta G, is pretty close to 0 kilocalories per mole, but it's favorable in the forward direction. Okay? Now this, go ahead.
Do you have to account for the fact that the oxygen is breaking away from two hydrogens, or is that?
You don't have to account for the fact that the oxygen's breaking away from two hydrogens, because it isn't. This hydrogen stays with the oxygen. So we're only breaking one oxygen-hydrogen bond. Yeah, good. Okay, you may want to know, okay, like what kind of energy differences lead to really, really favorable reactions. And this is why I prefer kilocalories per mole. If you look at this change in enthalpy for the reaction in kilocalories per mole, you can remember, and then I'll give you a rule of thumb. It's not particularly important, but it's kind of useful to know. A difference of 1.4 kilocalories per mole in free energy equals a factor of 10 in equilibrium constant. So if you want to memorize that 1.4 equals 10, what that means is if the free energy change for a reaction were minus 1.4 kilocalories per mole, the equilibrium constant for that reaction would be 10, meaning it's favorable to have products by a factor of 10. In this case, that number is, of course, if equilibrium, if delta G equals 0, then equilibrium constant equals 1. So you expect this equilibrium constant for this reaction to be somewhere between 10 and 1. Still favorable for products over starting materials, but not quite 10 times more favorable. All right, don't worry, I'm really not going to have you do, I mean, if you can add numbers to determine whether a reaction's favorable or not, that's fine. I'm not going to be really asking you questions about equilibrium constant based on enthalpies, but if you want to have a good feel in your head for how favorable a reaction's going to be, this is a useful number to know. Okay, let me show you just an example of bond breaking versus bond formation with ATP. So here is, you don't have to worry about drawing all of this. This will be in your notes. Here is beta-D-glucopyranose. You saw that when we were doing stereochemistry, or just glucose. One of the first steps in metabolism is for glucose to react with ATP to give you the following, in which the C6 hydroxyl of ATP is now, the C6 hydroxyl of glucose is now got a phospho group on it. So that's one thing that changes in the reaction. I'll draw for you real quickly the structure of ATP. Again, this is not for you to memorize at all at this stage. I'll make you do that in 352, so stay tuned. But I just want to illustrate this point that breaking bonds isn't what releases energy. It's the comparison of the strength of the bonds you break versus the bonds that you form. So here is part of the structure of ATP. There is a nucleobase there. We'll just call it A to save ourselves time, okay? In ATP, you're going to see that we break this bond, and we break, when we do this reaction, we're going to break those two bonds. We're going to make this new bond, and then we'll make another new bond in ADP. And again, don't worry about the structure of ATP versus ADP. I'm just making a point here. So you have two old bonds that you broke. You broke an oxygen-hydrogen bond, and you broke an oxygen-phosphorus bond. Then you make two new bonds. You make an oxygen-hydrogen bond, and you make an oxygen-phosphorus bond. And this is downhill in energy by a large amount, 1.78 kilojoules per mole. So that's much more favorable than the previous reaction was. That's big enough in biology, that's a big enough difference that this reaction is essentially irreversible. You can't go back. The primary reason for this is that the bond between oxygen and phosphorus here is weaker than the bond between oxygen and phosphorus here. That's stronger. There are reasons for that we will talk about. By the time we learn about it in 352, it will be obvious. You will look at that and you'll be like, of course that bond is stronger. Right now it doesn't make a lot of sense, but the point is we don't release energy by breaking this bond. We release energy by breaking that bond and replacing it with a stronger bond. Okay, you got that? Do you see the important distinction? Okay, that's thermodynamics. We need to now talk about kinetics, which is how do reactions happen? And kinetics is really important because if we understand how reactions happen, we can design new and better reactions, or we can take advantage of existing reactions to do new things. So, how do reactions happen? How reactions happens, that's just really terrible verb agreement there, but how do reactions happen? In what order are the bonds broken and formed? And also, how fast? So we're going to illustrate this with an example and probably review some things that you learned in general chemistry, but put it in a new and useful context. So here is a reaction between a molecule called cyanide, Cn minus, and an electrophile, which we're going to call methyl iodide. So Cn minus is going to be our nucleophile, and then our electrophile is going to be methyl iodide. Now that I've identified nucleophile and electrophile, based on stuff that you did for the first exam, you could probably already predict for me what and how, what's going to happen and how it's going to happen. But I'm going to show you basically how we know these things, and we're going to pretend like we have no idea what's going on, and we're going to use data to tell us what the mechanism of this reaction was. I'll tell you that the products of this reaction are H3CCN and then I minus. In general, when we're talking about reactions, we'll call these starting materials because they were the materials you had when you started the reaction. So that's really creative naming, and we'll call this products. We'll also, just so you're aware, we'll call the thing that leaves from the methyl group the leaving group, the thing that the nucleophile replaces. And this is an example of a substitution reaction. Now, I'll go ahead and tell you, if we look at bonds broken versus bonds formed, that this reaction is favorable. The equilibrium constant is much, much greater than 1. Delta G is much, much lower than 0, meaning this reaction is downhill favorable. It works great. And we're going to talk about that and about why that is in greater detail in Chapter 7. But basically, you would come up with that answer if you compared the strength of the CI bond that you're breaking versus the CC bond that you're making. That's a review of what we just talked about. But the question of how does it happen, what are the steps, and how fast do they occur, is an interesting one, okay? So you could hypothesize multiple potential reaction pathways. And we would use data to try to see which mechanistic hypothesis was correct. So let's just write down here what happens. We break the carbon iodide sigma bond and we make the carbon CN sigma bond. So those are the two things we have to that have to happen. Now, one mechanistic hypothesis number one is that we break the carbon iodide sigma bond first, we get an intermediate, and then we make the carbon CN sigma bond. If we were to draw this out in terms of arrows, now please remember this is a hypothesis. At the end I'm going to show you what the data actually say, but for right now we're just making predictions, okay? So for this option we break the C-I bond first. That would look like this. We would get an intermediate, and that intermediate would look like a positively charged carbon and then I minus, okay? Now, right now, based on what you already know, you can tell me whether you predict that step to be uphill or downhill. Just look at what we did. We broke a bond. We didn't make a new bond yet. So is that uphill or downhill? That's very uphill. That should be unfavorable, right? That's going from a lower energy starting material to a higher energy product. Along the way, between our product and our starting materials and what we're calling our intermediates, the cation and I minus, there would be something called a transition state. And the transition state is an energy maximum. And it would look like this for our molecule. We would have, the reaction simply involves the iodide leaving. And so the transition state is going to look like something halfway or midway in between the starting materials and the intermediate, where we're not quite at a full carbocation on the carbon. We're not quite at a full positive charge. And we're not quite at a full negative charge on the iodide. The bond is not completely broken, but we're pretty close to the way there. Okay? All right. So that's one hypothesis. And then the second part of this hypothesis would be that in the next step of the reaction, Cn minus comes along and attacks the carbon to make a new bond, and that's where we end up with the product, okay? Now, do you predict this second step? We have a first step and a second step. Do you predict this second step to be downhill or uphill? Downhill. Why? Because you're making a bond. If you had to look at the transition state for this step, it would probably look something like this. It involves a not quite positive charge on carbon and a not quite negative charge on Cn minus as we start to make the new carbon-carbon bond. Okay? We can actually diagram out this hypothesis on an energy diagram. Here is what you would expect. We're going to use this axis to be energy, and we're going to use this axis to be some measure of reaction progress. we could talk about that some other time. We're just going to make it be generic. These are our starting materials. This is our intermediate. This is our product. We predict overall that the reaction's downhill in energy, so the product should be lower in energy than the starting materials. We predict that the intermediate is higher in energy than the starting material. And then we could draw a pathway that would lead from step 1 to the intermediate to the product. This is step 1, this is step 2. And we'll say more about that next time. Now that mechanistic hypothesis doesn't actually end up being true, but we need to talk about why, and we'll get to that next time.